Hey everybody, this is Larry. This like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. 786 kth smallest prime fraction. What a mouthful. How's everyone doing? I just got out of or watching the Rangers game, hockey, New York's been very lucky this last couple of weeks. Hopefully it goes on. They've been winning. They just won, so that's why I'm a little bit cheerful. But I am also still tired. I'm always tired. I gotta figure out a way to not be tired for these. Um, but I did run like 11 miles or something like this earlier today, so I'm just a little bit. I don't know, just a little bit more everything. There's no error. There's nothing in here. But let's take a look at today's problem. 786 kth smallest prime fraction. Hope that intro. I don't know. That is got to be one of my weirdest intro. But that intro, beautiful Thursday. Hope everyone has a good weekend coming up. All right. So you're given a sorted array all containing one and prime numbers where all the integers of R are unique. You're also given an integer k. Okay, so they're unique and you're given k. For every I and j, we consider the fraction array sub I and array sub over array sub j. Return the kth smallest fraction considered. Return your answers in an array of integers size, array of integers of size 2 where answer 0 is equal to answer R, right? Okay, so basically you have and choose 2 kind of things, and then you're trying to figure it out. Okay, and I was gonna say something, but I was actually in my head doing something more, well, just like smart in general. But n is equal to 1,000 is interesting because that means that maybe we can do something faster. But we got to think about it as a breadth first search, right? Probably, or some idea that's related to a breadth first search. Maybe not quite a breadth, or breadth first search is the wrong one, but a shortest path, I think is the way that I want to say it. Sorry, not breadth first search, but a shortest path where you have heap, right? And basically, I think the core idea that I think that gets missed a lot. Maybe not. If you already know this, feel free to be like, Larry's an idiot. I already knew this. But the core component, the core part about shortest path problems or solutions or algorithms more specifically is that they are based on this idea of greedy, right? And this idea of greedy is just this idea of at every given iteration, if you want to call it that. I think it's technically like node relaxation, but I just call it. But for now, let's just say iteration. For every iteration, we get the distance that is smallest, or phrased another way, the node that is the distance that has not been relaxed, but is closest to our source node, right? I know that's why I didn't say it that way first because it's a mouthful. But okay, so that means that now we can play around with this idea, right? So we have k. K could be pretty big. Oh, better than O. I guess that is the follow-up. Can I? Man, I got distracted because I think my idea is n squared in the worst case. But so, all right, let's do it that way first, and then if I remember, because sometimes I just forget. Not gonna lie. We'll try to do it before n squared because I was actually thinking like, is there a smart way to do it n squared? I mean, I think if there is a way to do it, not n squared, I think it's going to be some binary search thing. To be honest, I could be wrong though. But that's just like a 2-second intuition. So I haven't really explored it. I don't want to explore it quite yet. So we'll come back to it, and then for you at home, you could skip ahead if you're looking for that part. For now, I'm going to do the n squared. Well, it's Is it n squared? Yeah, it should, I mean, should be n squared. Oh, I don't know. I mean, I think maybe it's actually a little bit slower, but is it n squared log? Yeah, it should be n squared log n, I guess, the way that I'm thinking about it. Huh. Oh, it is strictly increasing. Okay, so we don't have to. I mean, I was just going to sort it anyway, so that's not really a big deal. Okay, but the idea about what I said about greedy and all these things is that, you know, you start with one over, in this case, right? You start with 1 over 2, 1 over 3, 1 over 5. And we know that because it is in increasing order, the smallest number is going to be 1 over, you know, it's going to be in this direction, right? And then now when we go over 1 over 5, when we remove it and we maybe keep track of the numerator, so then now next is going to be 2 over 5, right? And then now we get this, the next smallest number. Okay, I over j. Okay, yeah. And then the next smallest number, right? This next smaller number is going to be, I think 1/3. I mean, it's really only a comparison between this number, the newly generated number, and this number. And this is 1/4. This is this is 40%, and this is 33%. So we're going to take this one and then we increment it, right? And then now we have this, right? And then the next smallest number is 2/5. So then we make it 3/5. And this is not just an increment, even though it looks that way here. It is going from 2 to 3, right? The prime ones. So then, and that's pretty much all the numbers, I think. So this is maybe not a great example, but yeah. And 1 over 2 will never get bigger. But I'm also not, I do wonder if there's a property. I mean, I think if we, you know, and maybe I'm already skipping ahead, but we're thinking about binary search. Do I always complete a row before going to the next one? I don't think so, because that doesn't really make sense. But yeah. But let's say we construct this thing, right? I mean, we don't have to construct it explicitly. We could construct this implicitly. How would we binary search this? Right? I mean, I think the idea with a binary search, I think it's going to be maybe I can. I don't know the n. I mean, I know the n square, right? It's just what we just talked about, and kind of. And unless I discover monotonicity about it, it's going to be n squared log n in a very naive way of doing it. I think the next thing that I'm thinking of, this is kind of hard for medium problem, is binary search, right? And binary search, it's kind of tough to be that exactly. Maybe, maybe not. I don't know. Like, I have a couple of ways of doing binary search. I don't know that this is quite ideal. But all right, I'm going to play around with the binary search one because I think that's the way that I, you know, that's the way that I have it now. But yeah, basically the idea here is going to be we have to, well, I mean, the component right is going to be the biggest, you know, the two number. So like in this case, it'll be 3/5 because that's just the two biggest number, right? So we have array of -2, and these are fractions intentionally. And then the smallest number is going to be, again, what we said, no, not that one. The first element over the last element, right? So then now maybe there's a cleaner way to do this with integer. And I'm not quite sure that I know how to do it that way. but basically and we're going to write like a binary search like this, but of course this is binary, so we don't even have to do it this way. We can just do it like a fixed iteration, maybe 100, right? Because yeah, each element is yeah, I mean basically we're bisecting 100 times, so that gives you 100 bits of precision, which is already probably too many because of various reasons, because the fraction in this case is going to be at most 3 times 10 to the 4th or whatever. So I mean that's not a prime number, but something like that's actually a really way of putting it. But yeah, so this gives you enough precision, my point. And then now we can do something like mid is equal to left plus right over 2 fraction, right? And then we go if good of mid, and what does good mean? It's just it's a thingy, right? Basically we're saying how many fractions, this is good if there are at most k fractions under this target, right? And yeah, and that's basically the idea. So if there are at most mid, that means we want to choose a bigger number, right? Because that means that target gives do I want at least k? Maybe I want at least k. Yeah, let's do at least k, right? Yeah, so at least small. So that means that if we have too many numbers, that means we want to try a smaller number, and we get a small number by moving the right bounds and so forth, right? And then now we have, but then now we have this fraction left, which is not quite what we want, but for now we'll just use it for debugging. It's not what we want because we want an exact fraction, which we can probably get, but it's not ideal to be honest. But yeah, but this idea now, then we can just go for an O of X kind of O of N kind of thing, which is that okay, count is equal to 0, and then now we just go over for I in range of for I in range of N, right? Then now we go for each one by one, and what we want to do is actually bisect. Am I getting this right? No, yeah, this is the big. I just want to make sure that I didn't mix up left and right, because this is the smallest number and this is the biggest number. And okay, so then now we want to get if array sub I is the denominator. Did I spell it right? Hopefully I spelled it right. How many numerators are there, right? And that's just a bisection thing, because so then now the idea is that okay, you have some array of, so your formula is going to be something like array of some random prefix over array sub I, where p is less than I. Right? So we want this thing, right? How many of this is true? And we get this is true by multiplying this on both sides. Unless it's possible that I'm messing up the signs. No, I think this is right though. Right, and now we have this number which we know for the given way. Then now we can binary search the upper bound of this. So then now, and array is already sorted, so we don't need to do anything funky. We just need to do something like this, right? Yeah. Oops, we have to do the array. And then now this is index. And basically, the number of numbers is going to be just I minus index, right? Because at index I, everything before that, right? So that means that if this is 0, then, wait. No, this is just index then, sorry. Yeah. So then something like this, right? Because that's where you would, is this right? This feels wrong. Was this fuse? Oh no, because target is a fraction. Okay, maybe that makes it right. I'm wary about off by 1, but I think the idea is roughly okay, right? Oh, at least greater than, so something like this. Okay, so I mean, for example, this is right? I mean, I didn't convert it back, and here you have 1/7 as well. So I think I mean, this is still very susceptible to off by ones and stuff like this, but the idea at least is validated, right? Because 2/5 is 0.4, and 1/7 is this number, and that's why I didn't want to do the other part yet. Is because if this is really wrong, then I don't want to write the code for it before finding out it's wrong. But now we know that we're going to be right. So yeah, how do I convert it back? I guess that is tricky, actually. I guess we can just do a new thing, right? So then now we're looking for, so left is going to be the answer, right? Or maybe we just do this, right? So then now we want the answer times array sub I, because we're testing it for each number. If this is the denominator, what is the numerator, right? Same thing that we have here. So now what is the numerator if this is the case? Well, we just bisect that bisect left again, right? Maybe that's not really the thing. So D for denominator, right? And then now we want to say this is going to be very sketch, right? But we basically have min error is equal to, I don't know, 1 year 100, doesn't matter. And yeah, result is going to be just like a blank thing. And then now we go, okay, so array of index over array sub I. We're going to compare this to our D. So yeah, so the current error is going to be this, and if error is less than min error, then error the other way around, min error is going to be error, and the result is going to be array sub I, array index. It's either that or I'm off by 1 on the index, to be honest, because I don't know if, because this may be, I think I want to check again for index and index -1, but for now I just want to see if it gives me something reasonable, right? Like, because, oh, whoops. Yep. Okay, so it looks good, but I'm still not confident about it. I think what I want to do is basically do the same thing, but with index is, we decrement it by 1. So that just in case that because there is some, when we deal with floating point numbers, nothing is really exact. So I want to be able to kind of look at to the left and to the right. Maybe we even need an index +1, to be honest, if I'm very sketched. I'm a little bit lazy though, and I think this is reasonable, and why not? I think maybe that's a good idea, actually. All right, so here, so then now index is equal to this for, let's call it J in range in index -1, index +1, right? Just so that we go all the cases. If J is within bounds, then we do this thing, and that's it. There. Now the code is actually tighter as well. Just to kind of cover my bases a little bit. Somehow that made it worse. Why? 1/5 to 2/5? What did I do? Oh, because I still have index here because I've just copy and paste one. Okay. So this looks good. Let's give it a submit. Time limit. Oh, apparently I did this 5 years ago. And I gave up on it. Huh. What did I do last time? I did it with heap, I think. Or priority queue. That is wild. Maybe 4 years ago I gave up on it. In C++ too. Anyway, okay, so I think this is one of those things that I am very worried about, or I was worried about. So let's play around with this, right? Let's print D real quick. Oh, well, with this thing. Yeah, 2 point. So 17 over 59 and 13 over 17. Oh, no, this isn't even close. Huh. Did I like messed up or something? J, no, I mean, min error we don't reset, so min error is 0, which is what I expect. Am I just like keeping track of the wrong things? J, did I like huh? I'm just confused, to be honest. 13 of 59 will give us that error. No, this is correct. So did I just like messed up? Like it's giving this. Oh wait, no. Why do I not 17? Oh no, this is what I give. Okay, so the expected, I misread the expected results, but it's either that or maybe this equal to count thing may be wrong then, because it looks like whatever we got from D, this part is right? So that means that this part is wrong, because it thinks that the answer should be this, but the answer is actually this, which is actually off by a lot. 6. All right, let's take a look real quick. Yeah, maybe there is some off by 1 here. But yeah, as you can see, like it converges very quickly. But there's only 4, so this is going to just return false the entire time. But that's not right, probably. So 0.288. The real answer is like 0.7 something, right? What am I doing wrong? 0, 1 has nothing. That makes sense. 13 is 1, which I guess makes sense. 17 has 2, right? 1 and 13. So I'm off by something here. Why is this returning 1? No, 17 only has 1. That makes sense, actually. So okay, so this is too small. And because it's too small, we want something bigger. What is wrong here? If this is too small, did I mess up K or something? Because we want something bigger. So why is that? What is our binary search doing? Is my upper bound wrong? Oh, this is wrong. Okay, I see. Wow. I'm wrong. Huh. Okay, I see it. Wow. I mean, okay, so we're not that bad. Because basically I made a wrong assumption that this number, so in this case 17 over 59 is going to be the biggest number, but that's not true. It's actually 13 over 17. I don't know what the right way to find this is, but we can also just make it an absolute upper bound. We just kind of messed this one up, so that should fix it. But that's a way. Wow. I didn't even re-examine this part, so that's pretty bad. I think I was just I took a shortcut there, even though Yeah. Okay. 1501. I forgot to post about it yesterday for 1500. Maybe I'll post it today. Let me take a screenshot. Yeah, I mean, I just forgot about to check my bounds. I just kind of did it very quickly and didn't think about it for. So what's the complexity here, right? I mean, here the binary search is going to be obviously O of 1 in terms of iterations. Technically, it's actually on the order of the number of bits, which is O of B, which I set the upper bound as, and the number of bits is actually less than 100, right? It's actually 60. So, but we can just say it's O of B for the number of bits. We do one good function here, and this is O of N for, oh, actually I lied. There are O of N iterations, but there is a binary search, so this is actually N log N. Technically, it's summation of all the log i's. Maybe that's different. I'm actually pretty bad about that. Log 1 plus log 2 plus log 3. I don't know if that's log n. Maybe I'm wrong, but still the upper bound is going to be n log n. And yeah, so it's going to be b times n log n, and this is just O of n to get the answer, and that's pretty much it. O of n times another binary search, but it's still dominated by this part anyway, which is O of b times n log n. Let me write it out. Where b is the number of bits in a number or whatever, in the max number if you want to call it that. And in space, well, we don't really oh no, this is the actual input. So this is O of 1, right? So O of 1 space, so pretty decent, pretty tight. And I have finally, I didn't even know that I attempted this 5 years ago, but I have finally defeated my demons from 5 years ago that I didn't know I had in time limiting theta. I just kind of gave up. I think so. Back then, I used to do these on stream on Twitch, just like random problems. So yeah, that's probably the context, which is why there probably isn't a video on this. I could be wrong though, but yeah. All right. That's all I have for this one. Let me know what you think. Let me show you the top of the code, and then the bottom of the code, and that's all I have. Thanks for watching. Hit the like button, hit the subscribe button, join me on Discord. I'll do another one after this. But yeah, thanks for watching. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.